Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. My name is Meshal Alhumaid. My group and I will present our senior project design today, which is mainly about autonomous management of home energy consumption. We are working with Professor Dr. Taleb Alawami in this project. First, let's talk about our outline. First, we will talk about the introduction, a quick definition of this project and some objectives. Then we'll talk about some relevant constraints and standards that we should follow. Then we'll talk about our load construction and the sensitivity. Then we'll address our suggested controller that all should be implemented in the demo. Starting with our project definition, our project is mainly about designing a controller that should solve the migration voltage issue by turning off some appliances from consumers' houses when there is a high demand on the grid. What appliances that will be turned off, that depends on the consumer's preference. So what makes this project unique, or what makes it important? In fact, by applying this controller and implementing on all houses, we should not be running out of electricity in all houses. Only some appliances will be turned off for a small period of time or until the voltage gets healthy.
Project objectives. Designing a simulation for controller that prevent voltage violations to save the system from over or under voltaging. Second, setting a priority. It wouldn't be nice if you're working on your essential device and just suddenly turns off while the least important device is still working. So we will make the customer choose which device to turn off first as a priority list. Third, adapting the controller with distance from feeder using sensitivity technique to have fair switching off between the houses. The voltage is not equal in the houses of the network, so we will use sensitivity to take action. Finally, making the process happens autonomously and via the National Electric Company to save time and effort and have a better results.
Assalamu alaikum. I'm going to talk about constraint and some relevant standards. Okay, any project have some constraint, whether it is time constraint, technical constraint, or cost constraint. In our project, we have time constraint, so we have to finish within 3 months approximately. Also, we have multiple technical constraints. The first one is that our controller must supply 220 plus or minus 5% RMS volt, because based on Saudi Electrical Company standards, the RMS volt supply to the consumer must be within the range of 220 RMS volt plus or minus 5%. Okay. Secondly, must operate on a frequency in the range of 60 Hz. Also, the controller must withstand and work on a temperature between minus 10 to 70 degrees. And in our project, we are going to limit our controller to four appliances only. Now I'm going to talk about some relevant standards. Okay. Before I talk about this standard, firstly, what is IEC? Okay. IEC is the International Electrotechnical Commission, which is a non-profit organization, prepare and publish international standards for many technologies. In our project, we are going to follow some of these standards. Okay. The first standards is to deal with the voltage not being more than 250 for single-phase appliances and 480 for multiple appliances. Second standards used for energy measured in loads or power metering and monitoring data, usually used for energy efficiency purposes. The last one specifies the requirement for power metering and monitoring device, which measure and monitor the electrical quantities.
Now we will talk about the power-related components in the network, which either generate or consume power. As a network generator, we will use AC voltage, like here in Saudi Arabia criteria, 220 RMS volts and 60 Hz. To model the impedance of the wires separating the houses, we will use resistance with a value of 0.0125 ohms. This corresponds to a wire of length 100 meters. Now we will talk about the loads. To simulate a water heater with a 3 kilowatt consumption, we will represent the water heater as a simple resistance, and since we know that power is voltage squared over resistance, and we have the nominal voltage equal to 220 volts, we'll use the resistance as 16 to have 3 kilowatts power consumption. Finally, we will represent air condition as induction motor. We can see on the left side of the induction motor that we have 3 input ports. 2 for supplying, which are input ports N plus and N minus. Third one is for torque needed, Tm. And we are taking out speed, voltage, torque. And this induction motor is 3 horsepower induction motor. From inside, in the induction motor, which we are using as air conditioner, we used a 3 horsepower motor, and we can see the nominal voltage, the frequency, the resistance, inductance, capacitance of the induction motor.
To make our system fair for all consumers, we implement the sensitivity. As you can see from the formula, sensitivity represents the ratio of the change in voltage to the change in power. So we are measuring how much voltage change do we have for a certain change in power. And this sensitivity will get higher as we move away from the source due to the impedance of the network. And to make use of the sensitivity, we use this formula that gives us EP value. This EP value represents the maximum power that I can supply the house with without overloading the network. And it consists of several parameters here, like alpha represent the minimum power that I guarantee the house to have without disturbing the system. Beta and K both are controller parameter that are going to use to tune the controller, and we have the sensitivity multiplied by the measured voltage minus the reference voltage, in our case 209, which represents 5% below the nominal voltage. The way we have implement the sensitivity in Simulink is by measuring the voltage and the current at the house to compute the power, then send the power and the voltage to the sensitivity controller. And we have used this block, which is 0-volt block, to resample the measurement to match with the sensitivity controller. And if we go inside this controller, you can see we are taking the power measurement and we take a delayed measurement, so we can compute the difference between this measurement, and we do the same to the voltage. And you can see beta, alpha, and VR and K, all of these parameters can be easily changed because we set them as variables, and we can change them to all across all the controller and the system in one place. And you can see here we have uold, which is a variable used to store the sensitivity value to update it when required. And I leave you now with my friend Meshal to discuss the code inside this block.
After we addressed how to calculate U, which is the sensitivity, we'll show you how to calculate it using our MATLAB code. Here is our MATLAB code. First, we will talk about some initialization. We have our power threshold value, that will be used as our first condition. Then we have the delta P and delta V, which is the power and voltage current values subtracting from the delayed value. Then we have our power base and voltage base value that will be used to convert our values to per unit. So let's start by our first condition, which will be about comparing our current power value to the threshold. If our current value is greater than our threshold, then we have to act. Otherwise, we have to assign the sensitivity value to the old sensitivity that we have. So if our current power is greater than the threshold, we have to check the other condition that we will have a negative, should have a negative sensitive value. So if our U or sensitivity is less than 0, then we will continue to calculate a new sensitivity. Otherwise, we will assign the old value of sensitivity to our sensitivity. So let's check here. If we have a negative sensitivity value or less than 0, we will calculate U, and we will check if the absolute value of subtracting the current value of U by the old U is less than the 1% of the old value of sensitivity, then we will have the same old value of sensitivity because there is no much change. Otherwise, we will continue to calculate the value of EB. We have one condition to calculate EB, which is our current voltage value should be greater than our limit, which is 209. If it's so, we have to calculate EB. Otherwise, we will assign 0 value to EB.
Taking action in the controller should be based on the values of EP to ensure fairness. But before taking action, 4 limits have to be calculated to ensure the fulfillment of the desired priority set by the consumer. The first limit is how much power does all 4 appliances consume together. The second limit is the total power subtracted by the power consumption of the appliance with the least priority. The third limit is the second limit subtracted by the consumption of the second least priority appliance. And the fourth limit will be equal to the power consumed by the highest priority appliance. We came up with 2 ways to implement our idea in MATLAB. The first one is to make a block that will take EP as an input, and based on its value, it will give a command signal to each load. This signal will be an input to the AND gate, and the second input is a signal that comes from the pulse generator to represent the consumer behavior of turning on and off the load. So if the consumer is turning the appliance on and the value of EP is within the acceptable level to allow the appliance to turn on, it will operate. In the first design, the limits that we calculated were used inside the block that we designed. In the second design, the limits will be used in the hysteresis controllers. If appliance 1 has the highest priority and appliance 4 has the least priority, the first limit will be used in the controller of the fourth appliance, meaning that whenever I cannot supply power to all loads without overloading the system, the last load will be turned off. The second limit will be used in the controller of the third appliance, and this will mean that if turning the fourth appliance was not enough to solve the problem, we will have to turn off the third appliance. And the same idea applies to the second and first appliances. The advantage of this design is that we have the ability to set a limit on when to turn our appliances back on. so it will make the design more flexible.
Due to the current situation with MATLAB license, we could not record our simulation, but we want to share some of our results during testing. We begin by the sensitivity result. As you can see, that sensitivity has increased from the first house to the second house. We can see from the graph that in the first house it reached a maximum of around 15 milli, where in the second house it reached a maximum of around 40 milli, and then was changing according to the load change. Moving on to the EP result, you can see from the figure that we have 4 graphs. First graph represents the power consumed by the house. Second graph represents the sensitivity of the house. And the third graph represents EP, change in EP. And the last graph represents the delta P, change in power. And we can see that EP is changing according to the change of power and sensitivity. So we can see if we disconnect loads here, the EP increases since we are disconnecting devices. Sensitivity will increase and will result in an increase in EP. And if we connect devices, like here we have to connect a big device, we can see that it will EP will drop. And if we connect more devices, that means EP will start decreasing and allowing less power to be consumed. And if we disconnect loads, it will allow more power to be consumed back. And this EP value will be fed to the controller discussed previously to take the decision of how many devices should be disconnected and from which house. This concludes our presentation. Thank you for listening.